It's time to talk about groups. What is a group? A group is a very important concept in abstract algebra. We won't be going into too much details with groups. There's a lot of theorems that are left purely to mathematicians, but it's good for linguists to know what a group is. So a group G, this nice fancy cursive G, consists of a set G and operation, which we call circle, and a group satisfies 4 axioms. So it's a pair with a set and an operation. We've seen this before, but there are 4 things that must occur in a group. First of all, G is closed under the operation, which means that if I have 2 elements A, B in our set G, then it better be the case that A dot B is also going to be in G. The operation is going to be associative. We already know what associativity is. I'm not going to explain it again, but it better be associative. The group has to contain one identity element, E. So in other words, if we have E and we use the operation with A, it's the same thing as A operation E, which just gives us A back. And for every element in our group, there better be an inverse. So we better have that G.G inverse is equal to G inverse dot G, and this just gives us the identity element back. Of course, if there's no identity element, we can't have inverses. So we'll talk about what those are called in the next video. So 4 axioms: closed, associative, identity, inverse. And we're going to check all of these when we do problems about figuring out whether things are groups or not. So one example of a group is addition modulo 3. In other words, the remainder of a number if you were to divide it by 3. So if we take 2 and we add 2 together, we get 4. We take the remainder, we get 1 back. That's how I'm going to explain it. If you want to know more about modulos, check out a discrete math course. For the sake of linguistics, that explanation is close enough to how it works that I think it's good enough. Okay, so we have to check first, is it closed? And how do we do that? Well, we make sure that every element is in Z3, and I'll tell you right now, Z3 is just the set 0, 1, and 2. And then when we do an operation together, so let's say plus in this case, on 2 elements A and B, it better come back into that set 0, 1, and 2. In fact, if we take a look at the chart here, no matter what we do, we end up with a 0, 1, or 2 back. So it is closed. That's good. 2. Is it associative? And I urge you to check yourself. I'm not going to go through it because it's really tedious to make sure all combinations work. But yes, it is indeed associative. The third one, which is a little more challenging to figure out, is there an identity? So in other words, what is the identity with the plus operation equal to? Well, we need to find an element that takes everything that's paired with back to itself. So a good place to start is 0, of course, because we know with addition, 0 is usually our identity element. So if we take 0 plus 0, we get 0 back. 0 plus 1, we get 1 back. 0 plus 2, we get 2 back. And similarly on the other line, 1 plus 0 is 1, 2 plus 0 is 2. So yeah, 0 is going to be our identity element. And finally, 4, is there an inverse for every element? Which means if we take 0 plus 0 inverse, we better get 0 back. If we take 1 plus 1 inverse, we better get 0. And if we take 2 plus 2 inverse, we better get 0. So what are these inverses? Well, 0, what takes us back to 0 is 0? Well, it's just 1. So it's just 0. 0 plus 0 gives us 0. What about 1 plus 1 inverse? If we have 1, what takes us back to 0? Well, 2 takes us back to 0. So the inverse of 1 is going to be 2. And if we have a 2, what takes us back to 0? Well, 1 takes us back. So every element has an inverse. The inverse of 0 is 0, the inverse of 1 is 2, and the inverse of 2 is 1. Therefore, it has an inverse, it has an identity, it's associative, it's closed. So this is a group. That's all it takes to satisfy these 4 axioms. In fact, this group is also commutative, which means that we can switch the order of things around, and we can tell that it's commutative based on kind of the symmetry here, but we can also check ourselves manually. And if it's commutative, then it is called an abelian group. So abelian here just means commutative. We don't say commutative groups, we say abelian groups. Of course, contributing to the person who discovers this. Historical note, not really important, but that's a terminology you should know as abelian before any of these things. Just means it's commutative as well. Okay, so here's a question. Is the group consisting of truth values 0 and 1 an exclusive OR a group? So of course this is the exclusive OR. These are our truth values. So the first thing we should do, of course, when it's small enough is just draw a chart. So we have the exclusive OR operation. We can have 0 and 1 as our first argument. We can have 0 and 1 as our second argument. What is the chart? Well, exclusive OR is true when the values are not the same. So it's going to be true when we have a 0 and a 1. It's going to be false when the values are the same. So our chart looks like this. So we have to check. 1. Is it closed? And if we take 0 and 1 and we put it with an operation and get 0 and 1 back, of course it's closed. We can only get 0 and 1 back, so that's good. 2, is it associative? You can check it yourself, but I'll do one example here. So if we take 1 exclusive OR, I'm going to write it with a different symbol just for the thickness of this pen. Is this equal to 1 exclusive OR, 0 exclusive OR, 0? So we can check these individually. Well, 1 exclusive OR 0 is just 1 exclusive OR 0. Is this equal to 1 exclusive OR? Well, 0 and 0 is going to give us 0 back because they are the same value. So it'll be 1 exclusive OR 0 equals 1 exclusive OR 0. So just be 1 equals 1. So with the one example we did is associative. In fact, if we did all of the examples, we would see that it is associative. So it is associative. You'd have to check it manually or find one counter example. So good luck. The third, is there an identity? So in other words, is there an E for exclusive OR? So is there something that always takes you back to its own value? And there is. So if we take 0 with 0, we get 0 back. If we take 0 with 1, we get 1 back. So our identity element here is actually 0. And this intuitively is kind of weird because you're like, well, it's just a matching thing. If the values match, you get false. If they're the same, you get it true. But the way it functions, the values it gives back shows us that this 0 is an identity element. So if we take 0 with 0, we get 0 back. If we take 0 with 1, we get 1 back. And that's enough to satisfy the identity element. Because whatever it goes with on the right, it gives it back. Okay, what about inverses? Let's ask ourselves if there are inverses for this. So what is the inverse of 0 and what is the inverse of 1? So what gives us back to 0? Well, if we have the same value, we get 0 back. So the inverse is just itself. So it satisfies all 4 axioms. Therefore, yes, it is a group. Okay, so groups that are commutative are called abelian groups. I just went over this. But some groups that you may want to verify yourself that are in fact groups are the real numbers and multiplication. So we know that 3 times 2 is equal to 2 times 3. It also satisfies other group properties. So for instance, if you take a real number and multiply it with another real number, you'll always get a real number back. Another example would be the universe of sets and intersection. So A intersection B is equal to B intersection A. In fact, I really advise you to check all of these and check if they're groups. So find the identity element, find the inverses, see if it's closed, see if there's any counterexamples to associativity. There shouldn't be. And finally, the third example with the integers and addition. Again, of course, we have that 2 plus 3 is just equal to 3 plus 2, and it satisfies all the other group properties. So again, please check on your own. It's a good exercise. This is probably something I'd put in an assignment just to check these things because, I mean, you've worked with these before, right? If you've been watching this series and you've been doing stuff in class, these sets are things you've been working with, or these groups anyway. So here's a theorem, and I'm going to do one proof because I think proofs are kind of important. And I kind of want to show you the reasoning for this. But it's a very important theorem. So a group has only one identity element. So you might think to yourself, I have a group here, and it has two identity elements. Well, if that's the case, something is wrong. Because there is only one identity element, and this can be proven for any group. So here is the proof. I'm just going to let G equal G and some operation be a group. Because our assumption is we're working with groups here. Okay, and now what I'm going to do is I'm going to assume that we have some E and E prime are identity elements. So I'll just call them identities. And the important thing here is that E is not equal to E prime. So they're not the same identity elements. That's why I'm going to assume this, and I'm going to show that if we assume this, we get some terrible contradiction. Okay, so what does this mean? Well, this means that E dot A is equal to A dot E, which is equal to A. And this means that E prime dot A is equal to A dot E prime, which is equal to A as well. So here's the clever part. In fact, to some people this may be super clever, for some people this may just be the most obvious and stupid thing you've seen, but for the sake of showing how this proof works, let's just assume that I have an element E on its own, and I'm going to start with E. Well, what is E? Well, if we take the identity element E prime and then use the operation with E, well, this is just equal to E, right? So this is the same, because this E prime is an identity element, so it should map E back to itself. But what do we know about this group? Well, identities are commutative. Identities will always be commutative, which means that we can flip around E and E prime. So we can take E dot E prime. Okay, so if we do the same thing as before, and we take this as the identity element, which maps the second one back to itself, we also know that E is an identity element, which means that it can map this E prime back to itself, which means that this is just equal to E prime. So we've found that these two identity elements are actually equal, which means if we have two identities and we assume they're not equal to themselves, eventually we come to the conclusion that, well, actually they are equal. Which means, by some contradiction in our reasoning here, that we can only have one identity element. Because if we have two and we say they're not equal, it turns out they're actually equal. So any group will have exactly one identity and no more. And we've proven this generally. So this wasn't proven for some specific group, this was proven for anything. So that's it for this video. If you have any questions, please leave them in the comments below, and I will do my best to answer them.